Pop culture cinema treats parallel dimensions as a cinematic trope, a convenient way for costumed heroes to cross paths with their alternate selves. The actual physics behind multiple realities presents a silent mathematical problem about the nature of our own existence. The mass of an electron, the strength of gravity, the specific charge of subatomic particles, every physical constant in our universe sits at a highly specific value. If any of these numbers were shifted by a fraction of a percent, atoms would repel each other, stars would fail to ignite, and biological life could not form. Statistically, the conditions required to build a habitable cosmos are practically zero. Looking at the raw data, the sheer volume of precise numerical alignments required to make Earth possible resembles a rigged game. Physicists rarely accept sheer luck as an answer. Rather than shrugging off our existence as a statistical anomaly, researchers are looking for a physical mechanism that guarantees those specific numbers had to occur. A structure containing infinite varying realities provides that exact mechanism. If every possible set of physical laws is playing out somewhere, a universe perfectly calibrated for biology becomes a mathematical certainty. Looking to the furthest observable edges of space brings us back to the immediate aftermath of the Big Bang. For a fraction of a second, the universe experienced a period of hyper-accelerated expansion. Cosmologists call this specific growth spurt inflation. Within a visible horizon, that rapid expansion eventually settled down. But researchers soon realized that out in the infinite dark beyond our telescopes, that explosive outward push might still be happening. This ongoing process would generate a sprawling cosmic foam. Pockets of space would continuously pinch off and swell into distinct, isolated bubbles. Each of these enclosed spaces would develop its own unique force strengths and particle masses. An endless supply of these bubbles directly resolves the mystery of our perfectly calibrated existence. If an infinite number of universes are constantly popping into existence with randomized properties, a bio-friendly environment like ours was bound to appear eventually. This foam model gives physicists something tangible to look for. Researchers are currently scanning the oldest light in existence, the residual heat left over from the Big Bang, to find empirical evidence of neighboring realms. This map of cosmic microwave background radiation captures temperature fluctuations of the early universe. Cosmologists are searching it for circular ring patterns, literal scars of bubble collisions. Isolating these anomalies proves our universe floats in a much larger bath of distinct realities. The deepest stretches of the cosmos are largely perceived as empty, dead space. The data suggests instead that it is an active, chaotic environment where completely different physical laws continually crash into one another. While cosmology looks outward, quantum mechanics points to a secondary, equally strange mechanism for parallel realities operating at a microscopic scale, right inside the atoms that make up human cells. At the subatomic level, unmeasured particles exist in a blurred smear of multiple locations simultaneously, a state known as superposition. Physicist Hugh Everett proposed that taking a measurement doesn't force a single outcome. Instead, the universe itself splinters, manifesting every possible outcome at once. Under this framework, the act of observation divides the observer. A human measuring a particle's position separates into multiple identical versions of themselves, each seeing a different result, completely blind to the existence of the others. The physics community struggles with this model because it resists standard empirical testing. We cannot cross the divide between these branching paths to ask the other versions of ourselves what they saw. We perceive time as a single straight line, moving cleanly from past to future. But at the quantum level, every physical interaction continuously fragments our timeline into millions of diverging, equally real outcomes. Knowing the mathematical probability of these parallel structures raises a practical question. What physical mechanisms would allow a human being to cross the void and enter another timeline? The physics required for interdimensional travel are not entirely speculative. The mathematical blueprints for a bridge between worlds have been sitting in plain sight since the publication of Albert Einstein's general theory of relativity. Relativity allows for the fabric of space and time to be warped. By gathering an immense concentration of matter, it is theoretically possible to puncture reality, twisting spacetime into a traversable tunnel known as a wormhole. The math holds up, but the engineering limits are severe. Warping spacetime requires generating and controlling a localized concentration of energy so dense it defies modern human capabilities. To open and stabilize a single wormhole, you would need to compress the entire mass of a galaxy into an area small enough to function as a doorway. Bringing that scale of matter into our solar system introduces an insurmountable physical threat. The gravitational pull generated by a galaxy-mass doorway would immediately rip apart the orbital mechanics of our nearby planets. The moment the tunnel successfully opened near Earth, the sheer gravitational force would instantly crush the planet into nothingness, long before a single person could step through to the other side. We lack the physical means to escape our specific timeline, or peer into the bubbles floating beyond our horizon. We are confined to this reality, an isolated pocket of space where the laws of physics aligned perfectly, allowing us to exist at all.